Now let's look at relative velocity, which is another application of vectors. Now if we look at the diagram here, now I want you to visualize this. This all makes sense if you visualize it, and we've already talked about it when we first introduced vectors. Now a girl is attempting to swim north across the river. Okay, so the girl wants to go north. So this is the direction she wants to go. So the girl relative to the river. Unfortunately, there's a current, and the current is an easterly current, so it's coming from the west going towards the east. So this is the current. So if you think about this, if you're trying to go to the north and you've got this current coming at you from the west towards the east, then of course you're going to end up going in this direction here, which is the final velocity of the girl. Now with vectors that makes sense. This is the velocity of the girl. This is the velocity of the girl relative to the river. This is the velocity of the river. So the velocity of the girl is going to be the velocity of the girl relative to the river plus the velocity of the river. This is your resultant. So in general, for relative velocity, the velocity of A will equal the velocity of A relative to B plus the velocity of B. Let's look at an example. Let I and j be unit vectors in the east and north directions respectively. Hamish is swimming in the ocean and his velocity relative to the water is given by the vector 2.5i plus 1j. The ocean's current velocity is VW equals 0.5i minus 3j. Calculate the magnitude and direction as a true bearing of Hamish's actual velocity, correct to 1 decimal place. So let's highlight everything. We've got the velocity of Hamish relative to the water. We've got the velocity of our water, and we want to find Hamish's actual velocity. That's going to be the velocity of h. Now in regards to a diagram, what's going on? We don't really need a diagram, but it's good for verifying whether we're doing it correctly. So if we think about Hamish, 2.5i is here plus 1j. So that's the vector there. So this is velocity of h relative to the water. When we're looking at the velocity of the water, that's 0.5i minus 3j, which is there. So this is the velocity of the water. So what's going to happen? Well, we need to move my velocity of the water across. So we can add our vectors. So we need to go across 0.5i and down negative 3.0j. So that's the velocity of the water moved across. So our resultant is there. That will be the final velocity of Hamish. Now without doing any calculations, if you had the diagram, you can see your answer. So if you're looking at that velocity vector for Hamish, I can use negative 2j and 3i. Should really draw that going all the way across. Okay, so I know without even doing any calculations that the velocity of Hamish is 3I minus 2J. Now, because our question appears to be using significant figures, I'm going to do the same. But let's do it using the formula. Our velocity of Hamish is going to be the velocity of Hamish relative to the water plus the velocity of the water. Now the velocity of Hamish relative to the water is 2.5I plus 1J plus the velocity of the water 0.5I minus 3J, and that is going to be 2.5 plus 0.5 is 3.0I. 1 take 3 minus 2.0J. And you can see that that equals what I got with the diagram. Now our magnitude is a square root of 3 squared plus negative 2 all squared, which is the square root of 13, which is approximately 3.6 meters per second to the minus 1. Our angle, theta, is inverse tan of y over x. Now note y is negative because our angle goes down, so we know our angle is going to be negative, so just be careful of that. So 33.7 degrees. So if we wanted it as a negative angle, it would be negative 33.7 degrees. The question asks for the bearing. So it's going to be approximately 90 plus 33.7, which is approximately 123.7 degrees true. Now note that angle is this angle theta there. Now you'll note that that's the same as that angle there because it's an alternate angle. You've got that Z. Okay, so just be careful, what is the question asking in regard to the angle? How does it want it? Finish with the therefore statement. So Hamish is swimming at approximately 3.6 meters per second -1 in an approximate direction of 123.7 degrees true.